In the last video, we presented a theorem and proved a theorem that will tell us the sum of a finite geometric sequence. And this is how we obtain the sum of a finite geometric sequence, or the sum of the first n terms of a geometric sequence. So for example, this is our geometric sequence. Let's say, for example, our task is get the sum of the first 7 terms. If we didn't know this, what we can do is we can add the terms one by one. So we begin with 6, we add 12, we add 24, then we add 48, then we add 96 until we get to the 7th term. But that is a lot of adding to do. And you would do a lot more adding when the number of elements in a geometric sequence is many. So it's a good thing we have your theorem, the theorem for the sum of a finite geometric sequence. The sum of the first 7 terms applying our formula is equal to 762. Now, what if the challenge to us is get the sum of the entire geometric sequence? It's no longer the sum of the first n terms. No. The challenge now is what is the sum of all terms in your geometric sequence? And you know, when you say geometric sequence, it is an infinite set. So you are adding an infinite number of terms. Is it even possible to get the sum? Well, it depends. It depends, and in particular, it depends on the value of your common ratio. So we can still use this. This is the formula to get the sum of a finite geometric sequence. But we can also use this to get the sum of an infinite geometric sequence, but we must pay attention to the fact that n here approaches infinity. Why? Because the number of elements in a geometric sequence is infinite. N here goes to infinity. So we will present a theorem that will help us get the sum of an infinite geometric sequence. We will no longer prove this. Given a geometric sequence, if the absolute value of your common ratio is less than 1, the sum of that infinite geometric sequence is this. It looks simpler. It looks cleaner because it is just equal to a sub 1 over 1 minus r. But this is true only when the common ratio or the absolute value of the common ratio is less than 1. On the other hand, when the absolute value of the common ratio is greater than or equal to 1, the geometric sequence has no finite sum. What does it mean when the absolute value of the common ratio is less than 1? R is a real number. It can be any real number. So we can graph that in our real number line. So when the absolute value of R is less than 1, that means R can be any real number between negative 1 and 1. It can be negative 1/2. It can be negative 0.1. It can be negative 0.9. It can be 0.9 for as long as that R is in this interval, negative 1 to 1. On the other hand, when the absolute value of your common ratio is greater than or equal to 1, that means R takes on values that could be greater than 1 or less than negative 1. So that is what we must pay attention to when we are getting the sum of an infinite geometric sequence. What is the value of R? Now let us investigate what happens to this sum when n goes to infinity and the absolute value of our R, the common ratio, is less than 1. So let's say, for example, our R is 1/2. 1/2 raised to n is the same as 1 over 2 to the n. Now, why are we computing this? Because this will go into computing for your sum. Look at that. That is this. N approaches infinity because a geometric sequence has an infinite number of elements. So let's say, for example, n is 1 billion. What is 2 raised to 1 billion? That's a big number. What happens when you divide 1 by a very big number? The quotient is almost 0. But 1 billion is not even infinity. Compared to infinity, 1 billion is nothing. And so you can now imagine what happens when n approaches infinity. This whole thing approaches 0. And so that term here in our formula vanishes. It disappears. It becomes 0. And the sum of our terms in a geometric sequence is now simply this. It is equal to a sub 1 over 1 minus r. However, when our r, for example, is equal to 2, look at this, 2 raised to n approaches infinity, 2 to the n goes to infinity. And so if you were to use that to compute for our sum, these are the things that can happen. The sum can go on to infinity or to negative infinity depending on the sign of your first term, or the sum does not converge to a particular value. The sum is like a swinging pendulum. It goes left and right, left and right. If that is what is happening to our sum, then the geometric sequence has no sum. The thing to pay attention to is the absolute value of r. Example. So this is a geometric sequence. R is 2/3. The absolute value of that is less than 1. The theorem says the sum of this sequence is a finite sum, even when n approaches infinity. I opened GeoGebra and I plotted the sum against the value of n. As n changes from 1 to infinity, you are producing a sequence of sums. Okay, so this one, horizontal axis stands for the value of n. The vertical axis stands for the value of your sum. So for example, when n is 1, your first sum is 3, S1. When you added the next term, you will produce a new sum. When you added the third term, you will produce a new sum again, so on and so forth. It doesn't stop. The sum continuously grows, but for this geometric sequence, there is somewhat like an invisible boundary. There is a limit to how far this sum will go. And I will introduce a new word for this. We describe Sn. This is a sequence of sums or sequence of partial sums. That is how we call it in calculus. And if you were to look at this, how do we describe this sum? It is converging. It is converging to a particular real number. And that number is in fact equal to 9. Now, how about this geometric sequence? The common ratio is greater than 1. What happens to this sum? So I opened again GeoGebra and plotted the sequence of sum that will happen when we added the terms one by one against the value of n. So when n is 1, this is the sum. When n is 2, when we add the second term, we get to a new sum. When we added the third term, it produces a new sum. Look at the behavior of our sums. The value of n has not even gone beyond 10, and yet look at our sum. The sum is shooting up very quickly. So we have a word for this. Sn, the sequence of partial sums, is divergent. It does not approach to a particular real number. This happens when the absolute value of the common ratio is greater than or equal to 1. So I will end this slide by presenting to you again the theorem, sum of an infinite geometric sequence. We have two cases. The geometric sequence can have a finite sum, which is equal to a sub 1 over 1 minus r, and that happens when the absolute value of the common ratio is less than 1. On the other hand, when the absolute value of the common ratio is greater than or equal to 1, your geometric sequence has no finite sum. And as n approaches infinity, these are the possibilities. The sum goes to infinity, the sum goes to negative infinity, or Sn does not converge to a particular real number.